Okay, so for this video, I'm going to be talking about the kind of like friction, cylinders, pulley, wedge videos, and I'm also going to talk about tipping and slipping problems because they're all kind of related. And what I mean by that is this question 2 on the 2018 final and this question 4 on the 2019 final. I'm going to actually do this question on the 2018 final, and then I'm just going to talk about the other question on the 2019 final. They involve similar concepts, so like both of them have a cylinder basically a pulley with friction that you're going to have to work with. But this problem involves free body diagrams for wedges, which I think can be a little more confusing. Whereas with the tipping and slipping problem, the free body diagram is a bit easier, and you just kind of need to know what you're looking for when you do a problem like that. So I'll start with this one, question 2. Like I said, I'm going to go through this one in its entirety. But the first thing I want to pick out while we're still on this screen is just what they're giving us. So they tell us the coefficient of friction for the rope and the cylinder. They tell us the mass of both of these blocks. And they tell us the coefficient of friction between contacting surfaces. And they're just asking how much can block A weigh without causing block B to slip. Something to note, when they say the coefficient of friction at contacting surfaces is 0.25, they mean at all contacting surfaces. That's just something to keep in mind when we go in and actually do this problem. So if I share my whiteboard, perfect. So the first thing that I want to do is draw a free body diagram for at least the blocks is what I'm going to start with. So this is going to be block C. So I'm going to have a normal force, which I'm going to call normal force 1, and then frictional force 1. And these are both between the block and the wall, obviously. I have the weight of the block itself. And then I've got a normal force, which I'm going to call normal force 2, and a frictional force, which I'm going to call F2. So this is block C. And then for block B, the pictures end up kind of using each other because we both have this N2 and F2 as well. There's also the weight of the block. I have the rope pulling, which is the tension 1, which is ultimately the force that we're going to need to take out of these free body diagrams. And then just so I don't forget, there's going to be a normal force down here, which I'll call N3, and a frictional force down here, which I'll call F3, just for reference. A lot of the equations I'm going to write down are in terms of variables. So if you see N3, if you see N1, just know what normal force, what frictional force I'm talking about for reference. So what we're really asking, like I said, is we're asking what is tension 1 in order to cause this block to slip. And then once we get that tension 1, we can look at the cylinder with friction and move on to the kind of dangling block to be able to figure out those values. But to start, we do need to look at these two. So if I open up a new page, something that we can note right away is we can relate friction forces and normal forces, right? We know that friction force 1 is just going to be equal to the coefficient of friction times N1, right? It's the same thing for friction force 2. It's going to be equal to the coefficient of friction N2, same thing for 3. The reason I say that right away is because this means that if we see both F1 and N1 in an equation, or we see both F3 and N3 in an equation, we're able to combine them and treat them like they're one unknown, which we need to do. So my next step is just to write out my summation of forces. I start with block B because that's the one where if I'm able to get tension 1 just from block B, that would be perfect. You end up not being able to, spoiler alert. But from here, let me just get my equation. So if we start with summation of forces in the X, we end up looking at something along the lines of negative T1 plus F3 plus F2 cosine 20 plus N2 sine 20. Something to note, these 20-degree angles are coming right from the picture. They basically showed us there was an angle of 20 degrees. And you could have, for example, this be sine 70, or sorry, cosine 70 instead of being sine 20. It doesn't matter. I wrote it in a way that I could use 20 for all my angles though. So from here, we can rewrite this a little bit, and I'm going to call this equation 1 how I have it written now. So we can say that 0 is equal to negative T1 plus 0.5769 and 2 plus 0.25 and 3. And like I said, the way that I got, for example, this N3 down here is by using F3 and the relationship up here. And that's the same way that I ended up combining F2 and N2, right? So this is in the X direction for block B. If I look in the Y direction for block B, so summation of forces in the Y is equal to 0 is equal to, I've got the weight of the block itself. I've got the normal force from the ground. I've got part of the frictional force. And I've got part of the normal force. Both of those are between the blocks. So I can also rewrite this one again. I'm going to call this equation 2 that I end up referencing later. So we'll say that 0 is equal to N3 is equal to negative 0.8542 N2 minus the weight, which is just 30 kilograms times 9.8. All right, so basically we've got our two equations for block B. We can look at those and we can say, hey, we've got 3 unknowns. Yeah, we got 4 unknowns, I think. Actually, we have 3 unknowns. N1 or N2, N3, and T1, but we only have 2 equations we're not able to solve. So instead we're going to go and we're going to look at block C. So if we look at block C, we're able to do the exact same thing. So we'd say summation of forces in the X is equal to 0. And I can say N1, which is that normal force from the wall, minus N2 sine theta, sine 20, minus F2 cosine 20. I know that I can combine N2 and F2. So I end up being able to write this equation, which I'm going to call equation 3, as N1 is equal to 0.5769 N2. And this is the first equation we've had that's kind of nice like this, if we're being honest. So now when we go in and we look at summation of forces in the Y for block C, it's equal to 0. We're able to say minus F1 plus N2 component minus F2 component minus the weight of the block as well. No, I didn't fit it on one line. And we're able to write this as equation 4. So I can say that 0 is equal to, if I rewrite this, actually plug in for the weight. So if I look back, I basically had 4 equations. They involved a variety of unknowns, but this equation and the last equation both have N1 and N2 for their unknowns. So if I have 2 equations with the same 2 unknowns, I'm able to combine them and solve. So if I basically plug in equation 3 to equation 4, I'm able to solve. And the values that you'll get out is you'll get out N2 is equal to 414.5. That's in newtons. And we're able to say that N1 is equal to 239.1 newtons. And we can then use these and go back to equations 1 and 2 that we had initially that we weren't able to solve. So if we use equation 2 and the N2 value we just got, we're able to solve for N3. So we can say that N3 is equal to 648.4 newtons. And then if we use equation 1, which had N2 and N3 as unknowns, we can plug in and we can get the fact that T1 is equal to 401.23 newtons. And this was a value that we were looking for originally and is the one that's going to let us relate the force needed on those wedges to the force that's going to be needed from the mass that's hanging. So if we think about drawing a free body diagram for that cylinder, it's because we need to consider tension around it. I'm going to call this T1 and this T2. Something that I know is I know that T2 is going to be greater than T1. And the reason for that is the block is hanging down here, right? If we think about it, the block's hanging and it's pulling down. So it's losing energy, it's losing force due to friction here. So this T1 then ends up lower. The reason that I'm pointing this out is because depending on what the equation sheet looks like, depending on what formula you have memorized, your T1 and T2 may be swapped from where I'm talking. So like you may prefer to write this as T1. When I say that, I mean you may prefer to write this as T1 and this is T2. And then you could say the exact same thing. It doesn't matter. You just have to make sure you understand which one's going to be bigger, which one's going to be smaller. So if I think about how we calculated forces on cylinders with frictions, forces on pulleys with frictions, we would say from my convention, we would say T2 is equal to T1 e to the mu beta, right? Where mu is a coefficient of friction, beta is the angle. In this case, beta is easy because it's just 90 degrees or pi over 2 radians. Because remember, we do have to plug in radians here. And they told us what mu is. They said mu is equal to 0.35. So from here, we have T1 from those summation of forces equations we solved for. We've got the U, we've got the beta. We're able to plug in and solve for T2 is equal to 220.59 newtons approximately. And then from here, we think about the free body diagram for the hanging mass. We've got the weight, and we've got tension too. So it's easy enough to say, oh, okay, that means weight is going to be equal to tension 2, and weight is just mass times gravitational constant. If we plug in 9.81 for G, we plug in T2, we end up getting that mass is equal to 70.87. I got in my case, the answer key says 70.89. They're not far enough apart that it's a problem. So that was a pretty quick run through of this problem. I obviously didn't show every substitution that I made. So if you're getting confused on anything, let me know. In terms of when I was actually doing the substitutions into the equations like in here, let me know if any of this didn't make sense. So I'm going to move back into the exams because I'm going to talk a little bit about the other problem, the other pulley problem that I didn't solve all the way through, just to make some points with it. So if you give me, there we go. And then here we are. Okay. Perfect. So like I said, this problem is what I just solved fully. Hopefully that made sense to you guys. And then just talk a little bit about what's going on in this question 4. This is going to be a similar problem in terms of what happens over on this side, right? Because we're still basically going to have, hey, the weight of the block is going to be the tension of the rope. We're going to have to use the fact that the coefficient of friction is 0.25, find the angle, all that stuff. The angle I'm actually going to talk about. But this is more or less what the same thing that we're doing on this left side of the problem. Where things actually change is what's going on over here. Because they're asking for basically the range of cylinder mass, which corresponds to the range of tension values in this rope, this is where we just need to consider two situations. We need to consider this block sliding or getting pulled this way across this plane. But we also need to consider this block tipping, right? This block rotating about this front point, basically. So those are the two scenarios that we're gonna have to go off of. And we need to check both of them to see, hey, which one is the tension smaller? Because what we really know is that the smaller tension is gonna cause the block to tip, right? So that's gonna be the maximum weight we can put on here. So if I go into my old set of notes, these basically discuss the types of friction problems that you'll see. So you'll either get a problem where nothing ever ends up changing, which is what we actually want in this problem, right? We don't want the block to slide, we don't want the block to move. We may also find that no matter what we plug in, or if we know the specific mass value, that we're gonna get motion. The other thing we might see is we might not know and we have to check. This is more what we have to do in this case. We're gonna have to check and see, hey, what is that mass value gonna be to give us something? So if we look at what it actually means for a block to be slipping or tipping, when the block tends to slip, we know that we have a frictional force, we still have a normal force. So those are all things we need to consider. And basically, this block's gonna slide when the applied force, which they call P, is equal to the frictional force, right? Because once that P overcomes the frictional force, the block slides. So that's the first situation that we need to look for. The other situation that we need to look for is when we get tipping. So the other scenario that we kind of have to look at is if the block is going to end up tipping. We know it's going to tip around the front corner. In our case, it's also this corner right here. So what we say is we know that the entirety of the normal force is acting on that corner because it's the only point of contact. And we know that all the frictional force is also touching that corner because it's the only point of contact. So if we were to take the moment at that point, or about that point, down in that lower left-hand corner, there's really only two forces that we need to worry about, the weight of the block itself and then that applied force. So in our case, we'll have the weight of the block itself and then the tension. So those are the two scenarios we're looking at. The other thing that I wanted to discuss in regards to that problem is what the beta value is around here. So if we think about, I'm going to reshare the whiteboard just to talk about it. But what we basically have is we have the pulley itself, we've got a rope and then it comes down below the nice 90 degrees basically. So I know that if the rope went straight out sideways like this would be 90 degrees, right? So in reality, what I have is I have 90 plus whatever this angle is. So if I call it alpha in this case, and we know how to get this angle because they told us what angle this triangle was. I believe they said it was 3, 4, 3. Let me pull up where I did this work before I end up lying. Yes, it was 3, 4, 3 like that. Or sorry, 3, 4, 5. So this angle right here, they're the same. They're, what are they called? Alternate interior angles, something like that. But we can see that they're the same angle. So if we're able to find that alpha is equal to 37 degrees approximately, we know that beta is equal to 90 plus alpha, or beta is equal to 127 degrees. We should remember that we need this in radians. So we can go pi over 180 to convert that. I got a beta value of roughly 2.22 radians to be able to plug in. So that was the only other thing that I wanted to touch on with these problems. Biggest thing is understanding what we need to look at. In this case, we've obviously got tipping and slipping. If you want an example of that, there should be a link in the description of this video. And you can use that Jeff Hansen playlist I've been linking a lot. I believe he does at least 1 or 2 example problems. He also has example problems on wedges and screws. If you want more of that, he should have some kind of belt or like cylinder friction problem as well, if you want to take a look at those. I'll link all those in the description of this video for you guys. But yeah, that's it for this one. We should be good.